So now that we have looked at the differentiation of inverse trig functions, we want to look at the integration, or the antiderivatives of each of these. So there are three formulas we want to look at: arcsine, arctangent, and arcsecant. Arccosine is just going to be the same thing as arcsine, the only difference being it will be negative in front. Arccotangent is the same thing as arctangent, the only difference being it'll be negative. And arccosecant goes with arcsecant, it'll just be the negative version of arcsecant. So if I look at what these formulas are telling me, all of them are going to end up probably being a u substitution problem. And so that's how we get the u and du. So we are assuming u is a differential function of x, and this a represents a constant that is going to be a positive constant number. So on the first one, arcsine, you would be looking at the integral of du over the root of a squared, which is a constant, minus u squared, and based on the derivative, that is going to be going backwards to arcsine, but it's going to be u over a plus c. So if you think about the derivative, we didn't have that in the derivative formula, and if you need to recall that, you can go back and watch my YouTube video over inverse trig functions differentiation. The reason being, with the derivative formulas, we started with a 1 minus u squared, but with the antiderivatives, we're saying we can look at another constant other than 1, and that's where this divide by a is going to have to come from. If it had just been 1 squared, or technically 1 minus u squared, that would just be arcsine of u plus c. Now with arctangent, this is the one that does not have the root. You're adding the two squares together, and so it's going to be arctangent of u over a, but because of the way that the chain rule works and everything, you have to have a 1 over a out in front. You don't have that with arcsine. Arcsecant also has that 1 over a in front. Notice though it's a little bit different than the derivative formula. The derivative formula had the absolute value of u in the answer before the root u squared minus a squared. Dropping the absolute value in the integrand just puts it inside the answer over here. So you're going to have 1 over a, arcsecant, absolute value of u over a plus c. And that'll also help restrict the domain here. So like I said, u is a differential function of x. All of these are going to have to be u substitution problems. A is a constant that is greater than 0. So our first example is very basic. What you want to do is really focus on pattern recognition. Try to determine, okay, what is the pattern of this integrand and which of the three formulas does it match? Well, in this case, I have a root, so it narrows it down to either arcsine or arcsecant. Since I have a constant minus the function of x behind it, that's going to go back to arcsine. So what I need to do is pick apart the pieces here. I need to determine what is a and what is u. Well, in this case, my a came from a squared minus u squared in that square root. And so in this case, a is 2 and my u is x. Then du is dx, which I see in the problem. So if I rewrite this integral, I have the integral of du over root a squared minus u squared, which is arcsine of u over a plus c. And so then I just need to go back and fill in the spots. So I have arcsine of x over 2 plus c. That would be the antiderivative of this original problem. So here's another one pretty similar to that. Notice we are adding in the denominator. I do not have a root in the denominator. I have a constant plus a function of x being squared, which means this is going to go back to arctangent. So first of all, your a, this came from a squared plus u squared on the bottom. So my a is actually root 2. It's not always going to be a nice whole number. U would be the root of 9x squared, which will go to 3x. But then because this is u substitution, I have to take the derivative of u to get du, which is 3dx. Now notice, in the original problem, I only have dx. I do not have that 3. So here's where I actually go into regular u substitution. I'm going to put in the 3 that I'm missing, divide by 3 on the outside. Then if I go and find my antiderivative, I have 1/3 out in front, times, this goes back to the formula for arctangent, which has 1 over a in front. So I need 1 over root 2 arctan of u over a, so 3x divided by root 2 plus c. And then of course I could rewrite this as 1 over 3 root 2 arctan of 3x over root 2 plus c. So looking at the pattern here, notice you have a function of x out in front before the root, a function of x on the inside minus a constant number. So this is going to match the pattern for arcsecant. So again, pick out your pieces. So a would be the square root of 9, which is 3. U is going to be the square root of that 4x squared, so 2x. Du is 2dx for the u substitution. Now notice, with arcsecant, we are supposed to have u times the square root of u squared minus a squared. I don't have that in the denominator right now because I don't have a 2x out in front. But what I'm going to do is I'm just going to go ahead and go on with the u substitution and see what happens. A lot of times it'll just fall out with the u substitution and all work out in the end. So with the u substitution, I need to put in a 2 on the inside, divide by 2 on the outside. Well, there's a property of integrals that says you can actually move constant numbers that are being multiplied inside or outside of the integral depending on where you want them. Since I wanted 2x on the bottom for that u out in front of the root, I'm actually going to move this back onto the inside. That way I have that 2x all together. So let me erase this part. And I'm going to move that 2 into the inside. And notice I'm not actually changing anything. I'm just multiplying by 1 in disguise, but I'm forcing everything to fit what I need it to fit for the pattern of the formula. So I'm going to go ahead and rewrite this. So I have the integral of du on top over 2x is u, root u squared minus a squared, which goes back to 1 over a, arcsecant absolute value of u over a plus c, and then I just need to fill in all the missing pieces. So I have 1 over 3 arcsecant absolute value of 2x over 3 plus c. That is my antiderivative. Those were pretty easy though, so let's look at a harder one. So notice this one almost looks like arcsine. We have the constant minus a function of x being squared, but the problem is I have this random plus 3 in the numerator with that x, and I'm not really sure what to do with that. There shouldn't be an x plus 3 since u in this case is going to have to equal x. So what I need to do first is realize a lot of times you have to rewrite an integral before you can actually solve it. So what I mean by that is I can actually rewrite this by splitting the integral as x over root 4 minus x squared dx plus the integral of 3 over root 4 minus x squared and then dx. This will allow me to take care of each individual part separately. So the first one right here, I have x over 4 minus x squared inside that root. That's actually going to be a regular u substitution problem. I can make u the inside of the root, that'll take care of the x on top with the du. Over here, this is looking like arcsine. So with the first one, I'm going to deal with this part first. U would equal the inside, 4 minus x squared. Du would then be negative 2x dx. Notice in the numerator I only have x dx, so I need that negative 2 on the inside, negative 1/2 on the outside, and then that will fit u substitution perfectly. With this one here, I'm going to make that into arcsine, so my a is root 4, which is 2, and then u would just be x, du would then be dx. Don't be alarmed that there is a 3 on top. Any constant number that is being multiplied that I don't need, I can just pull out in front as a coefficient. So that's not going to cause an issue here. So now if I rewrite this, I have negative 1/2. The integral of negative 2x dx is du over the square root of u plus, I'm going to pull that 3 out in front, integral of du over the square root of a squared minus u squared. This first part you can go ahead and rewrite to make it a little bit easier on yourself. Rewrite that as u to the negative 1/2 du, and then that can be easily integrated. So I'm going to go ahead and move up everything a little bit. So now if I find my antiderivative, I'm going to switch colors. I have negative 1/2. This antiderivative of u to the negative 1/2 is going to go to u to the positive 1/2. Divide by 1/2 is the same thing as multiplying by 2. So the 2's are actually going to cancel out. And then I have plus 3, and the second part here turns into arc sine. So I have arc sine of u over a, and then 1 plus c behind everything. So then I just need to go back and fill in all the missing pieces. So I have negative, I'm going to go ahead and change that to parentheses u, and that u was 4 minus x squared to the 1/2, plus 3 arc sine of the u for the second half, which was x, over a, which is 2, and then plus c. Now, on this last example, this one's a little bit more perplexing. When I first look at it, it does not fit any of the inverse trig formulas. It doesn't look like arctangent, even though it doesn't have a root, because arctangent would have to have a function of x squared plus a constant squared. That doesn't fit this. It can't be arc sine or arc secant because I don't see a square root. So then I start thinking about other methods. I could think about u substitution, but my u would have to be the denominator, du would have to be whatever is in the numerator. That doesn't fit. So I've kind of exhausted all my choices and options here. So then I start thinking about doing some more complex things, like maybe completing the square or rewriting or things like that. In this case, I can't rewrite, but I can do completing the square. So I'm going to go ahead and complete the square on the side and then rewrite the integral. So x squared minus 4x. I'm going to take half of negative 4, which is negative 2, then square it, becomes positive 4. If I add 4 to the front part, then I have to subtract 4 at the end. This is all getting grouped together, and my goal is to get that to factor into a binomial, perfect square binomial. It does. I get x minus 2 being squared, plus 3 at the end. So now if I go back and rewrite my integral, I have the integral of dx over parentheses x minus 2 squared plus 3. Well, what do you notice? Now it actually fits one of the patterns. I have a function of x being squared plus a constant, all in the denominator with nothing else on top. That forms arctangent. So my a would be root 3. My u would be x minus 2. Du is dx, which is perfect because that's all I have in the numerator. And so if I rewrite this, I now have the integral of du over u squared plus a squared, which goes back to 1 over a, so 1 over root 3, arctan of u over a, so x minus 2 over root 3, plus c. And that's my antiderivative. So hopefully that helps you out in understanding how to integrate inverse trig functions.